All right, so let's go ahead and jump into some cool little random graphs. So what you can see in front is going to be one of these kind of just initial starting things. So it's going to be some smattering of zeros and ones in a chaotic fashion. And then we're going to take this thing and we're going to feed it into this next generation algorithm as many times as we feel like it. So the first little thing is going to be to construct this random graph. So you can see that I'm going to have this buffer of all zeros around the outside, which was my just lazy way of implementing this game of life. If you have a better version of that, you obviously wouldn't need this buffer of zeros, but it'll work for us right now. So when it comes to constructing the random thing, I'm also going to give it the buffer of zeros as well. So it's plotted, it looks chaotic, it is whatever it happens to be. I'm going to run this thing through 20 generations. So if we let this reset itself, you can see that process re-evolve. So it's there, and then it slowly morphs into the end. This particular run's got what? Kind of a nice little square at the bottom. I think I have the final version of it drawn here. So it does have what? This little square emerging. We have this other still life that's going to emerge on the bottom. These things in the middle then are still swirling and moving and doing some chaotic things. A thing to note is just because you're currently a still life doesn't mean you're going to be stuck there for forever. If you look in this run, at some point in time, we had some of these nice little boxes, but then if stuff kind of runs into it, that box might just devolve into nothingness afterwards. I guess we also have another box down at the very bottom that right at the very end changes from being a box into nothingness as well. So in that one, we have my original version, which is purely random to start, or at least somewhat random. It's about a 50-50 split between zeros and ones. After about 20 or so generations, we're down to only about 19, or I guess about 18% of them are going to be alive. If we up the ante a little bit, you can kind of see that same type of structure emerge as well. So here we're going to have an initial grid, which is 2 to the 8th by 2 to the 8th. Same bit of random start construction. And if you zoom in on this, you can see maybe some clarity. If our screen has enough going on, you can see a bunch of zeros and ones, looks somewhat chaotic at the very beginning. I'm going to not print out kind of the evolution on all of them. I'm just going to hit go 20 times and then hit go another 20 times to then see what's going to emerge after year 20 and then ultimately after year 40. So in this setup, it went from having about a 50-50 split initially down to about 16 or so were alive after 20 years and down to about 12-ish or so were alive after 40 years. And that's going to ebb and flow, obviously, as things go down, but it's clearly not staying at about that 50%. We're launching down into in the teens-ish or so, but it is somewhat dependent upon what our starting state happens to be. And that really begins kind of the starting place of the multitude of questions that exist in the background. So this is where the game of life gets a lot of fun, and it's a fan favorite of most people's because it's relatively easy to implement. You get all these cool little animations that emerge, and it begins to really kind of pick at some interesting questions of like, all right, well, that got me to that final state, but what other starting places might end up there? If you give me a starting state and a different state, will that one ever be achieved? The answer to that second question is actually no. It's actually part of the undecidability of this game of life. So it's this little line right here, which says the game of life is undecidable. So that is, if you give me an initial state and some other random pattern, I want to know if there's going to be some algorithm that's going to tell me that these two things are actually linked. And the answer to that is no, we actually can't do that. It's connected to the halting problem back in the world of Turing machines. And there's a ton of overlap between Conway's game of life and the world of Turing machines, in that this game of life actually has this power of one of these universal Turing machines, which tells me that anything that can be computed algorithmically can actually be computed within the game of life. So it's so-called Turing complete. And there are a bazillion other follow-up questions. As I mentioned before, it is this fan favorite. It's also a fan favorite of mine. I remember way back when I was first learning to program and looking at some of these early versions of Game of Life that you initially just start having all of these questions revolving in your head. And you're like, well, can I do this? Can I do this? Can I do that? Can I do this? Can I do this? And one of Conway's early questions was to think about if it was possible to have one of these little machines or these little games actually continually generate stuff so that it could have an infinite amount of outputs. And originally, he actually thought that that was not doable. He conjectured that there was no such pattern. So this question of, is there going to be some type of cannon or something that can constantly keep on shooting out things over and over and over? He thought that that was not actually possible, that there was no such pattern that could grow indefinitely. So later on, Bill Gosper at MIT actually was able to design one of these little initial states that would continually generate things for all eternity. This little cannon, which is now known as the Gosper glider gun, or this glider cannon, is this little image down below. So it starts off with this thing. So it looks like it's got a couple of these little squares on the back end. And what's going to happen is that between these, there's going to be this morphing of left and right. And as these things sew together very nicely, they're going to constantly kick out gliders. And it's going to indefinitely kick out gliders over and over and over. In this particular animation, I have a bottom endpoint in that I don't have this infinite dimensional array at my disposal. So you're going to see little gliders drift off to the bottom right. But if that were to continue indefinitely, obviously they would never run into anything. They just keep on marching along. And it's one of my favorite little animations to see, just because it's somewhat mesmerizing of just like watching this thing go back, left and right and left and right. So you have those two little squares, and there's going to be essentially these little starships that are dancing between them. And as they merge back up on the middle, they do kick out this little glider, which you can see then marches off down to the bottom right. And then it's going to kick out another glider, which marches off down to the bottom right. And then it's going to kick off another glider, which is going to kick off down to the right. And that would happen indefinitely, but that would never stop. So the conjecture that Conway had that this was not possible was obviously proved false, in that the existence of one of these glider cannons shows that you can generate something that will continually evolve, which is part of the really chaotic structure of this game of life, is that we have a machine that can then give rise to more machines. And then if that bigger, more complicated machine could give rise to additional cooler, better machines, it just snowballs out of control as from there. So if you did watch that little Numberphilia video, he does mention a little bit about these glider cannons. It's actually off drawn in the background of this little thing dancing around. And you can see that once you have it hand coded, which is the hardest part of designing it, you can easily feed it into this little animation world, and you can see this little mesmerizing glider cannon in action. In Sage, it's still not super smooth. There's a little bit of glitchiness going on just because it's got, it's got 2,000 or 200, I should say, little generations that are being stored, and then it's constantly pasting those. There are a bunch of really nice sites that allow you to play this game of life in a very fast fashion. So I'll have a couple other links to these so that you can kind of doodle around a little bit and then let the system just evolve in a much faster and a little bit more chaotic fashion. But for now, we're going to jump back to the notes and start looking at a couple interesting underlying questions and poke into them a little bit farther, just to kind of, I guess, wet our whistle a little bit to kind of get excited about some of these things. And then I'll let you play around with them a little bit more in your activity. So we'll give this a pause and then we'll jump back here.